Okay. So, fitness, selection, and population management. A lot of this stuff we've already kind of been talking about informally. We've been thinking about these things. I've been planting seeds in there. So you might find a lot of this to be like somewhat review, which is a great thing. So hopefully it doesn't bore you. So, fitness selection, and population management. We're just going to talk about a couple of ideas. So, this is what we're talking about in terms of selection. Who do we pick for the parents, right? How are we going to do this? Because based on what we were seeing before, always picking the top one, always picking the best is actually kind of a terrible idea because you'll converge way too quickly. Your population will become overrun with the best candidate, but the relative best candidate is going to be garbage in terms of the grand scheme of things. So, there's two big driving forces we care about here. Your diversity and like your selection pressure. I mean, they're the same thing, it's just these are the ideas connected to how we do our selection. The selection pressure would be, and this is not from a biology perspective, so I apologize to any biologists in the room. It's just we stole that term, like everything else here, and then we misuse it. But selection pressure is how much like of a bias there is towards something being selected. So in TSP, those with a higher fitness, well, there's like a higher, like those are the ones where there's like a higher selection pressure on those, because they're the better ones in terms of what we want to optimize. But there are a lot of things we could do there are a lot of things we could emphasize in terms of selection pressure, which we will talk about. I think at the end of this we'll talk a little bit about novelty search, which is really interesting. So selection pressure is how much pressure there is on picking a given individual for some reason. If you always pick the top candidates, your selection pressure, that's cranked up to 11, and it's a terrible idea because you have no diversity in your population. You need diversity in your populations, otherwise you'll converge way too quickly. That diversity, just because a candidate solution isn't as good as that one, doesn't mean it doesn't have a lot of valuable information that when passed on can become that much more meaningful or effective in the context of whatever we're doing. So variation is important because selection pressure, it's a good thing, but we need to rein it in. And variation, diversity, that's a good thing, but we also have to rein that in a little bit too, because otherwise we're just going to be randomly looking at things and we don't really have any encouragement to good ones. Yeah?
So you're saying we should be using stuff other than just fitness for selection?
No, all I'm saying is there are other things we could do and other things we could incorporate. But what I'm saying is when we pick or when we come up with, or maybe we're inventing a new selection strategy on how to pick the parents, we need to be cognizant of, well, we want to make sure we're encouraging diversity while also encouraging selection pressure, and there's that balance. That's all I'm saying. And a lot of this you probably kind of discovered empirically. When doing your TSP one, did you ever like play around with how big, like raise your hand if you did like tournament selection. Raise your hand if you did basically what I did in the video, where you just like picked the top K, or you picked K and then picked the best one of the K. Okay, yeah, that's tournament selection, okay. So we will formally talk about it. So that's very common, but when doing it, did you ever play with that number of the pool size? And you may have gotten a sense that as you make the pool size smaller, it might decrease selection pressure. But if you make the pool size bigger, meaning it's more likely to have a really good one there, then you end up having really high selection pressure for good ones, but then you end up kind of ruining your diversity. It's that balance you gotta play with. And you have empirically, if you were playing around with those settings, you have observed this without having a word for it, let's say. So selection, this stuff, it's a differential survivor of individuals based on fitness values to compete for resources to take part in reproduction. So compete for resources could mean a lot of things, but in the example of the TSP, the GA, you probably did a not Steady state GA, meaning that the resources is basically having a spot to exist in the population if you have a fixed population size. Being able to reproduce, that's like, well, the selection pressure. How likely are we to pick? Like, we want to pick relatively good ones, but we don't always want to pick the best ones. So, generational, there we go. This is the one. I kept calling it like discrete. Generational, not steady state. This is what I was doing. This is typically what I do because I'm lazy. You have your population, you create a new empty population, and you recreate the whole population, and then you use this for your next iteration, and so on, and so on, and so on. That's generational. It's kind of like the world exists, we hit pause, the next generation comes. Pause, the next generation comes. So replace the whole population. Population size of mu. I'm going to use these symbols because this is what the symbols are formally and in the textbooks and whatnot. Realistically, you will never think of population size as, oh, mu, that's the mu value. Just be aware that that's what it is in the context of these slides or the textbook. Has anyone downloaded the textbook or obtained the textbook? One? All right. It's a pretty good textbook, I'm just saying. Especially if you're doing a lecture, you know, it might be a good resource. And then there's some number of offspring are produced, lambda, and the whole population of size mu is replaced. So this is the idea for the generational model. Then there's steady state. This is where we have a population size of mu, but some number of offspring are produced, lambda, where lambda is going to be less than mu. Lambda is going to be probably far, 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 far less than mu. Basically, we have our big population, and we're going to have like a small number here, and then we're going to replace that small number in the current population. So I'm not making a whole new population. It's like me telling you, like imagine it was that row there. That row, the second one from the back, just because it's really full. If I was doing generational, I would make copies of you and then put you in the next row. And then you'd all be obliterated and disappear. Instead, with this is, I'm going to pick two of you, maybe you reproduce, and then I put you back in that same row. And I keep operating on that same one pool of things. Over time, the things in that pool change. But now this is why they call it like the steady state one, is you kind of get a sense of like, well, it's not like you're hitting pause, whole population's replaced. Pause, whole population's replaced. Now it's kind of like, well, you know, the pool, the one single pool is changing a little bit over time. There's generational gap. I don't think I've ever seen this word used anywhere outside the slides in the textbook. So I'm just showing you them because that's what they're called technically. But you probably get a sense so far in this course that we're pretty loosey-goosey when it comes to our terminology and our strategy. And that's probably a consequence of the culture of anything evolutionary computation where it's like, well, how do I do selection? I don't know, do whatever the hell you want. Because there's no right way. And that's why I love this. It's hard to be wrong. Your results could be crap, but you won't be wrong. So selection, remember, selection is based on relative individual fitness. All that means when I say that is, if I have a population of 100, and I pick K, let's say 5, and I take the best one of the 5. I pick the best one relative to the other ones. Think of yesterday, was it yesterday that we did the TSP thing? Yeah, think of yesterday where, look, I don't know what the optimal solution was for that thing. But the ones that were the best are the ones that are relatively the best. So it's not in this like absolute sense, it's all relatively speaking. And selection works independently from the problem and the representation. And this independence, I mean, you could design a selection that isn't independent. I'm certain you can come up with one where it's really tuned to your problem or representation or something. But typically the idea here is we need a way to pick good ones and who's going to get chosen for reproduction. And that's usually based on some summary statistics, maybe like their fitness value, maybe the level of diversity they add to the pool. There's a lot of things we could include, but we pick based on that. We just select them. The fact that I use like tournament selection on TSP, tournament selection has nothing to do with TSP. It has nothing to do with the fact that the encoding was just a string of cities in order. Yeah?
What do you mean by a solution is good relatively?
It's like, I don't know, like with yesterday, I don't know what the best permutation was. But I know what the best one we had in here, it was over there. It was you, right? You were second, it was you. So you got the best one, relatively speaking, relative to everyone else in this room. But in reality, there might be someone in the next room that's just obliterating everybody. Maybe the best score is like 7. And we got like 100,000 or 200,000 or something. So relatively, like we picked the ones that are relatively good. So selection takes place in 2 areas. One, and you might get tricked into thinking it only takes place in one area if you're like me and you do the generational strategy. Because we need to select who the parents are. That's one of the areas, and then the parents may or may not have crossover done to them, and may or may not have mutation done to them before they go into the next generation. I guess their offspring going to the next generation. Because remember, based on it, like if there's an 80% chance of crossover and a 10% chance of mutation, well, there's still a chance that those parents that were selected, nothing changes about them before they go to the next generation. It's possible, right? They just kind of get left alone. So the selection of the parents is one thing, but when we're dealing with steady state, we need to decide, okay, we select who the parents are, but who do we replace? If I want a fixed population size, and I have a steady state algorithm where I'm always modifying the same ones, if I pick 2 parents, do I may or may not modify them and just have them replace themselves, like go back to where they were? Or do I want to like pick these 2 and then say, well, who do I replace? Do I go basically do the opposite, pick K and pick the worst 2 and then replace those? I don't know. But this is where the other half of selection can come in if you're doing steady state evolution. Any questions about that? Because a lot of times, like I'm usually talking in terms of generational because I just always do that. There's nothing wrong with steady state. In fact, maybe it's better. It's not. But because of that, you might kind of lose the fact that, well, selection might need to take place on the other end as well. It's just when you're doing generational, you don't really need to think about it because you just fill up the population. So sky's the limit. Do whatever you want for selection on who gets replaced or not. Whatever, doesn't matter. So select, okay, I guess this is written in a way that's kind of like the inverse. Select who survives. Well, I was kind of wording it, select who doesn't survive, but you get the idea. So parent selection, this will always be a thing, whatever. Most versions of evolutionary algorithms has some mechanism of this. So although some versions don't have particularly sophisticated selections, they do have a selection strategy. But what we need to think about is the operators. Again, it's defined as the operators. Well, really what that means is how we define the selection probabilities. How likely are we to pick any given candidate solution for reproduction? And then the algorithm is, well, how are we using that information for our selection? This is just a fancy way of splitting the selection algorithm apart into 2 core ideas that, to me, I always kind of think of as an atomic idea. They kind of go hand in hand. It's hard for me to separate them, but technically you can think of it that way.
Can you expand a bit on the difference between operators and the algorithm here?
Don't worry about it. Really, it's just selection. That's what I was just saying, is it's hard to kind of pull these things apart because really it's the selection strategy has 2 things to it. It's like, well, there's the probabilities of who gets selected, and then there's the actual selection that's based on the probabilities. But I just like to think of them kind of as like one big thing. So parent selection. Fitness proportionate selection. So there's a lot of fitness proportionate selection. So probability an individual I being selected for mating depends on its absolute fitness value compared to the absolute fitness values of the whole population. You could replace this with relative if you want, but what they're doing here is, they're making it absolute fitness, which really isn't a good word to use here because it's awfully misleading. But they're basically taking, imagine you took the fitness score and then you made it so you found the biggest one, and then you divided them all such that they were all ranging between 0 and 1. The sum of all the things should be 1. That's a whole bunch of crap you don't need to think about, when in reality, what we're going to do is, oh, look, fancy math. So, a lot of times computer scientists love putting stuff like that in there, which this isn't even overly complex. It's the fitness over the sum of the whole population's fitness. Great. But you'll notice a lot of times, especially if you read like academic papers, computer scientists love putting math in there to make it look like they know what they're doing, and it's not just them digging around with code, when in reality that's all we're doing. If you haven't discovered that yet. We just add the math to be like, no, trust us. Right? It's more serious. Yeah. So parent selection, fitness proportion selection, there's drawbacks. Good candidates might take over the population way too quickly. That's the premature convergence. When you crank up that fitness, or when you crank up that selection pressure, which is very easy to do when you have one of these strategies, it might have way premature convergence. But you can also have very low pressure when there's a very similar fitness values. Imagine you have a whole bunch of candidate solutions. Let's say you have 100 candidate solutions for TSP. And all of their fitness scores are basically the same, but their permutations are entirely different. That's possible, right? That's very easily possible. All their fitness scores are pretty close to one another, but they represent entirely different paths to take. So imagine one of them might be a good one to really select for mating. They'd be a really good one to select, but because the way you've designed it, because it's based purely on the fitness, and the fitnesses are all relatively the same, there's going to be very little selection pressure for the one that we might actually really want to pursue. Again, also keep in mind that this is a contrived example. This is me explaining a scenario where somehow magically we know what's going on in the back end. But if you put your hat on like I was during my PhD of like, well, how do I choose to find the best nonlinear function describing brain activity? I don't know what that, you just try different things and you hope for the best. Yeah?
Could one example potentially be like in TSP where you, instead of looking at fitness, you might look at literally just two different cities, see if you have like a really good one between two different cities or something?
I'm not sure what you mean.
I guess individual small pieces of the traversal.
Oh, so you kind of yeah, sure, why not? So what he was saying is, what if you have fitness, basically that would require you to have a slightly different fitness evaluation, where instead of taking the fitness as a whole, maybe you start to look at if there's 1,000 cities, maybe I'll look at fitnesses as 10 windows. Maybe it's not a sliding window, it's just 10 windows. Or maybe you do a sliding window or something. And you just have a different strategy for fitness scores. That could totally work, yeah. But that's more of a how to evaluate fitness question so much as selection. Whatever. Windowing, sigma scaling, again, fancy words to mean we just need a way to pick one, and this rank-based selection, okay, fitness-based, let's have a look at this example. So we have a fitness for F. A is 1, B is 4, C is 5, sum is 10. Now we scale them such that they're between 0 and 1. So basically, if I'm selecting parents, I have a 50% chance to select this one, 40% chance to select this one, and a 1% or 10% chance to select that one. You can scale it if you want. Why? Just because it might have an effect. What if you just add 10 to all of those values? Now it sums to 40, and then you do the division again. Notice how, by doing that, we actually kind of normalize the selection. It becomes less extreme, but by doing this, all we did was a linear scaling. We added 10, but then when you do the probabilities again, it kind of flattens it. And maybe you like that. Maybe that's very beneficial. And then look what happens as you add more. It becomes that much more even. So if you're finding that the strategy you're using has way too much selection pressure towards the good ones, if you did something like sigma scaling or windowing, something as simple as just adding some value to it and then taking the proportion, you can kind of even the playing field. Now, how much you want to do that? Well, you don't want to do it too much. If I added 1 billion, the fitnesses are going to be the same until times 10 to the negative 6. 9 times 10 to the negative 9, so it's useless. But, point being, we have a mechanism to adjust this if we want. So this is effectively kind of like another tunable parameter. Where like, well, I've got that, but now I can just maybe, okay, I want to kind of flatten that selection pressure a little bit so it's not as extreme. There is rank-based selection. So this tries to address the problem with fitness proportion selection, which is okay, well, you gotta, yeah.
So are you able to tell if there's too much selection pressure when something converges really fast? Is that one of the ways?
That's usually what I would do. There are a whole bunch of things you could do. You can get really fancy if you want, but usually my thing is run it a couple of times and be like, you know, it looks like it's converging way too quickly. Yeah. And when I talk about early premature convergence, I'm going to draw a plot of what I mean. Premature convergence would be something like this. Oh, very, very rapid, and then it like peters out, you know, and there's really very little, right? What I mean by non-premature convergence, it's possible that something like this happens. Right, and then it's basically the same. But maybe this one's population became overflowing with no diversity. Not the best way to word it. But there's no diversity anymore, and it's basically just mutation having an effect at this point. But if the population's more diverse, it might take longer to converge, but if that's happening, it also might be the case that you end up getting way better over time. But you don't know. Remember, there's nothing, before you hit run, you don't know what any of this is going to be. You might have some intuition, but at the end of the day, if you're ever thinking, but how am I going to know what you're not until you do it? Plot it, see what happens. It looks like early convergence to me. You know, I'd look at this and say, maybe it's early convergence, but I don't know. Maybe the next time I hit run where I'm like, let's lower the selection pressure. It just kind of goes like, I don't know, maybe it just sucks. All right, so maybe I need a little more selection pressure. And then it goes really quickly, but it's better, I don't know. And then there's the fact that there's so much randomness involved, stochasticness involved. Remember, we don't like the word random. It has a bad, what, pardon?
Bad rap.
Yeah, it's got, thank you, I couldn't think of it. It comes with baggage, right? Because the people are like, oh, it's just a random search. Well, no, it's definitely not, because selection pressure exists. So we don't really know. There's a lot of the stochastic stuff taking place too, where I could have the exact same settings and I hit run, and maybe I get a nice distribution of results that looks nice like this. Or I might hit run, and then my distribution looks like, right? Where it's like every time I hit run, I'm just getting wildly different results, even though my parameters are basically the same. It's entirely possible. Remember, think of the fact that these aren't problems that we know what to expect, that we're actually using here. So yeah, rank-based, it tries to address some of the issues that we get with the proportional one. It still has kind of like the proportional feel, but selection probabilities are based on like a rank and not fit directly, direct fitness values? I don't know what I was trying to say there. But it has a lot of overhead. There might be some issues involved. There might be some computational overhead with the selection strategy, which has a downside. There's no free lunch, right? So linear ranking. Let's have a look at this example. Fitness 1, 4, 5. All right, put their rank. 0, 1, 2. And then what is this? P cell, P this, P cell R, P LR. I guess this would be picking the inverse best one?
Gotta love acronyms.
Yeah, I know, right? Cell LR, cell linear rank, probably that one. FP, FP, fitness proportional. P, select fitness proportional, right, that's what this is. This is select with linear scaling, where we do a scale of 2, where S is 2, we get values of this. Oh, and I guess we're maximizing fitness score. And then here where you can change S. I'm rediscovering all this stuff as we go too, because let me put it this way. In practice, no one in evolutionary computation thinks about this stuff. Sorry. No one thinks about, what I just said is very incorrect. We all think about this stuff. We never think about this stuff this way. We're always going like, oh, okay, we want to scale it somehow. Let's just do this. Half the time you'll reinvent the wheel. Because again, remember all of these things are like, well, what's S? Well, that's a tunable thing. And what's mu? Well, mu is the population size, so you have a way. These all might be ways you kind of come up with without even thinking about it. There's no exam, but this would be something I would say like, that right there is not on the test. No one in their right mind would put something like that on the test if they ever actually do evolutionary computation stuff. Remember, we use evolutionary computation because we're lazy. Yeah.
Even if we don't have to care, I'm still curious about what P is.
P is the selection probability. So the P selection, this is the FP. That's going to be the fitness proportion. And that's why it's the same here, 1, 4, 5. 1, 4, 5. This is the ranks. And then this is how you would calculate the linear rank strategy. And I think this is where linear rank, again, with a slightly different S. All it means is, with the rank-based strategy, like the fitness proportion, where we had a strategy of kind of like flattening that selection, same idea here with this rank-based one too. Rank-based exponential. Okay, roulette wheel. Roulette wheel and tournament are probably the only two you will ever see in practice. Roulette wheel is the idea of, let's say I have fitness, can you see this kind of? Individual 1 has a fitness 1, 2 is 2, 3 is 3, 4 is 4, 5 is 5. That's easy. You add them all up, divide them by it, and then you get a value between 0 and 1 for each of them. And then you plot it. The sum is 1. It's a percentage. The sum is 100. And then you imagine you spin the wheel, you get a random number between 0 and 100, and then you see where it lands. That one gets selected. But the bigger piece of the roulette wheel, the bigger piece of the pie, as your fitness goes up, you get a bigger piece of the pie. Very popular. It's kind of fun to think about how you might implement this. If you're ever like, and I'll just show you the easy way to do it, because sometimes you get it in your head about like, okay, I gotta do, there's probably an easier way to do it. Does this work? Perfect. All you do is, let's say I had this right here. And so 1 has 7%, 2, 13%, 3, 20%, 4, 27, and 5, 33. So this is 20, 60, adds up to 100, good. So here's what you do. I like decimals, I don't like percents. So we'll do it this way. And the reason I like decimals is because when you ask a computer to give me a random float, it's going to give you a number between 0 and 1, so it's perfect. So here's what you do. It's difficult to be like, okay, so if I roll, all you do is you say, okay, so if I get a number between 0 and 0.7, it goes to 1. If I get a number between 0.7 and 0.13, it goes to 2, right? If I get a value between, a value between 0.7 and what? 0.2, yeah. So this goes to 1. This is 0.20. So you just sum it as you go, but then it has to fall in that range, right? So this is 20, and then this would be 47, and then, wait, I skipped something. I skipped the 20. 40, 67, 100. So, there we go. So if it's between 67 and 100, we pick 5, 4, 3, 2, 1. Questions about that? The only reason I showed you is because I know sometimes students are like, wait, so how do I implement that? I gotta get all, just sum them up as you go and then just check the ranges of where the number falls and you're good to go. It's one of those things that you look at and go like, yeah, that's obvious. But before you do it, you might end up kind of tripping over your own feet. That's why I showed you. You like your way better. What's your way?
It's basically the same, but the idea is you start by choosing a random number, and then for each point you kind of subtract it off.
Yeah, it is. Yeah,
Basically.
it's exactly the same, just that way. Good though. Yeah. So roulette wheel. Oh look, I show you. Perfect. There's an algorithm. Roulette wheel. So in general, if you take lambda spins, it doesn't. This is one of those things that might be hard to wrap your head around. Remember, lambda is how many we want to select. Mu is the whole population. If you take lambda spins to select lambda candidate solutions for reproduction, the problem is, and this is going to be one of those things that's hard to wrap your head around unless you're very familiar with statistics and probability, that what I would do, and Ethan saw me do this yesterday, when I have a hard time wrapping my head around things where it's like, what would that mean? Like if I change this, is that really going to change the distribution of the results I get? When in doubt, simulate it. I did that yesterday in lab because I wanted to know, like, how do I select 2 points the best way? Do I pick between 0 and 1 and take the minimum and the maximum? Or can I select 1 point and then say pick a point between this point and the end? Is that the same? It's not. And I answered it by just running a test on my computer in Python. I said run like 1,000 times, plot the results. Way different distributions. If you're to do that here, you'd observe that you get really bad results if you take lambda spins. Instead, what's a good thing to do in practice is take one spin with lambda arms with equal spacing between them, and that gives you a much better distribution of results. It might be, let me draw what I mean. There's no eraser. And what sucks is I have an eraser in my office and I'm like, I'll put this in my bag, I can use it. And I never do. Here's my roulette wheel. And it looks something like this. Right? If I spin, maybe it lands here. I spin, maybe it lands here. I'm going to do, like if I need to pick lambda parents, I can spin this lambda times for my lambda parents. So far so good, right? If you do this, you end up getting perhaps way too much selection pressure here. You don't get a nice, good distribution. Instead, what you do is if you want to select like 10 parents, you will say, okay, we'll start at 0, and then what I'm going to do is if I have 10 parents and they need to be between 0 and 1, what I'll do is I'll spin it, and then for the first one it'll be the value that I spin, and then it'll be the value that I spin plus 0.1, and then the value that I spin plus 0.2. You basically have 10 arms. Pick a different color. 2, 3, 4, 5, 6, 7, 8, 9, 10. Pretend those are evenly spaced. You spin that once, and then you go, okay, that's my selection. This gives you much nicer results in practice. Yeah?
So say an example where we actually need to like select, say 100 people, population, whatever.
Yep.
What, in your experience, what would the difference be between spinning it once with 100 spots compared to spinning it like 10 times with 10 spots?
10 times with 10 spots? Oh, that's an interesting one. I don't know, I've never done that, but that's an interesting question. So to ask his question again so everyone hears it, he basically was like, well, what if you kind of like go in the middle? If you need to select 100, you're telling me don't spin 100 times. You're telling me spin once with 100 arms on here. It's totally doable, but kind of, that's just going to be pure proportional. But what he's suggesting is, well, what if you don't do 100 spins and you don't do one spin, you do 10 spins of 10 arms? I don't know. My intuition would say probably somewhere in the middle in terms of better, worse, it'll probably be different. Once again, classic evolutionary computation of like, I don't know, see what happens. You had a question?
Yeah, well, kind of skip with the room really short.
Sorry, I can't really hear.
I'll try to speak louder.
Okay.
So could you do something like Bayesian statistics and like update the amount of spins that you do with like if we have like a dynamic population size, have the amount of slices change so that the probability remains as like uniformly distributed?
Well, but if you have it too uniformly distributed, you might not have enough selection pressure. But if you take that idea and massage it a bit, usually if you ever have a question of like, could you do this? The answer is yes. Try it. Do it, and then you'll get extra marks on the assignment, extra points on the assignment, right?
Yeah. And then the other question was, you say it's better to have lambda spins or lambda slices for like a spin, but wouldn't you want to have maybe more selection biases, something that's more present, because then that would mean that genotype is stronger, which is like the basis?
Yes, but then you might end up having too much selection pressure. So it's always that balance of like, well, if you do it with this spins, I think what it is, you get way too much selection pressure. Where you do it the other way, it helps address that problem. Maybe in the problem you are currently working with, based on the results you've been getting, you do want to crank up selection pressure. If that's the case, awesome. Maybe you don't want it to be that much higher. You might do what his strategy is, which is interesting. Yeah.
So does doing multiple arms change the selection pressure up then?
So here, the best way to answer this is to do a simulation. So if we had more time, we could whip it up right here to see empirically. Because I always like seeing. I learn better when I do it and see it, right? So maybe you're like me. We don't really have the time to do that right now, but.
Yeah, I'm definitely sure.
All right, roulette wheel, here's some code. Tournament. Realistically, roulette wheel and this is the most popular. This is the most popular. Why? Because it's so easy. And it works well, and it's easy to adjust for selection pressure. You want more selection pressure, increase the pool size. You want less, decrease the pool size. That's it. When in doubt, go to this. That doesn't mean use this on your assignments always. This means, in practice, this is what people use, but if you want to explore and play around, you want to invent something new, go for it. But this is what people usually do. Pick K, and then take the best one of that. There are some interesting properties here. If K is 2, the worst candidate solution actually is never capable of making it to the next generation. Because imagine I pick the worst 2, I'll take the better one. The worst one can never actually make it. If I pick 3, the worst 2 can never make it. So as you increase K, you are effectively killing off K minus 1 of the worst ones guaranteed, unless we happen to randomly change back to something like that was that. But it's an interesting note. How much of an effect this has in practice? It depends on the problem, it depends on the situation, but that's kind of why, like a lot of times you'll think like, oh, well, if K was equal to mu, and then I take the best one, I'm always picking the best one. If K is equal to 1, well, I'm just randomly picking. But I'm sure you have the intuition towards like, well, as I increase K, I'll increase selection pressure to the good ones because I'm more likely to pick good ones. But the other side of that is you're also guaranteeing that K minus 1 of the bad ones, like the K minus 1 worst ones, won't make it. So it's kind of, you can think about it both ways. Yeah?
Agree with me because I'm not used to tournament, but is K the pool size
Yeah, K is pool, yeah. Tournament, there's some code, it's the easiest. No need to evaluate all candidates. This is actually a huge win. If I have 100 chromosomes, or let's say I have 1,000 chromosomes, and I need to do TSP evaluation. When you ran your code, what was the thing that took the longest in general? What was the thing that took the longest? Did anyone profile their GA?
Selection?
No. Hopefully not.
With really large pool sizes, it took a long time.
Okay, yeah, that would, and it would, okay, you might have done it this way, but the worst thing is fitness evaluation. That's the slowest part. So if you have a population of 1,000, and then you want to do roulette wheel, you have to know the fitness of every candidate solution. If I have a population of 1,000, but I only pick K, I can evaluate those K, I'll remember what those K's fitness is, and then I'll pick K more, odds are I'm not going to actually have to evaluate all 1,000. I'm going to get lucky and repick the same ones, and I'll save a little bit of time. That's awesome. That said, if you're using elitism, which you should, you're going to have to still evaluate everybody. Yeah?
If it's the fastest, then what would be the time and complexity of tournament selection compared to like other selection methods in general?
They're still going to be linear.
Okay.
They're all linear. So here's a quick little thing. And I suppose we can end with this. Let's see. Tournament selection probably of individually selected depends on, yeah, we just talked about this. Uniform selection, don't do that. Survivor selection, okay, we'll pick up here next time. But I'll end with this. Every once in a while, someone will ask, like, okay, well, what are we talking about in terms of computational complexity in terms of the genetic algorithm? Don't ask that question. Because we can ask and answer the questions about the computational complexity of the individual parts, like evaluating. Let's talk about the TSP example, and that we did yesterday. I gave you a list of coordinates. What's the computational complexity of generating the distance matrix? Come on, guys. Is it n? N squared. You have to cut everybody to everybody else. It's n squared. So that's quadratic. What about evaluating a given candidate solution? Did none of you think about the complexity of your algorithms? Come on, guys. You need to geek out about your algorithms more. What is the computational complexity of calculating the fitness of one candidate solution? Linear. You start at the beginning and then you just look up in the table and you get to the end. What's the computational complexity of doing the whole population? Linear squared? Well, not really. It's actually hairy because, yes, it would be, right? It would be like k times n, where k is the length, like the size of the population, and n is the length of the tour, right? But realistically, like k is probably still going to be a constant, technically, because we're not going to have these these hilariously large k's. We might have populations of like 1 million, but it's going to be 1 million. You know?
When you say K now, what are you referring to?
The population size. Oh, yeah, I realized the mu.
I actually said linear still.
Oh, linear still, yes. Okay, it's effectively linear, yeah. But like, it does depend on one of those parameters, but those parameters are still kind of like constants. I can change them, just a sec. And then we have selection. Well, selection is pick K and take the best ones. So that's not, that's going to depend on K. That's just K. I realize the issue now of using K and whatnot. I'm reusing the variable. And then the genetic operators, well, depending on what it is, if it's just something like randomly pick a point and do like a swap, well, that's constant time. If it's something like a reverse, like an inversion mutation, well, that's going to be linear because you got to like start and then reverse them all. Crossovers are probably going to be linear. But all of these things don't have bad computational complexities in and of themselves. The long run times come from the fact that some of these numbers are big. And if you have a population of, like when I was doing my GP thing, and when I was doing my GP thing during my PhD, warning, when you do the GP assignment, do not even think about using parameters anywhere near what I'm about to talk about, because my GP system was designed for these hilariously large numbers. The one you're going to use from deep is not. So you're going to have small population sizes and a relatively small number of generations, and it'll still take a hell of a long time to run. But I was doing I had a population size of, I don't know, probably it was 10,000 times 7, so 70,000, and I let it run for 1 billion generations. So how many times was fitness evaluation done? 70,000 times 1 billion. That's a lot. I mean, it is just, at the end of the day, it's constant. Because all of those values are still fixed depending on, it's still it's dependent on how long is the tour, right? Obviously that matters. But in terms of how long it runs, the quadratic thing, which is a pre-processing thing in the case of TSP, that's not what matters in the runtimes here, in a practical sense. You had a question, but we are out of time. What's your question?
Wouldn't the overall time complexity of the algorithm be brought down by generating distances if that's n squared? Because then wouldn't it
You only have to do it once.
right, but you still have to do it.
Yeah.